Hello, in this video we are going to investigate the following problem on the topic of calculating limits using integrals. Evaluate the following limit. L equals to the limit as n approaches infinity of the sum over k goes from 1 to n, 1 over n times 1 plus 21k minus 20 all over 3n to the thirds. Pause the video at this point and give it a try. On the next slide, I will show you the final answer to the problem. If you don't want to see the final answer yet, please pause the video now. The answer to the problem is L equals to 45 over 28. If this is not the answer you got on the first attempt, please pause the video again at this point and give it a second try. The first thing to do for solving these kinds of limits is to be able to interpret the sum as a Riemann sum for an integrable function over an appropriate closed interval corresponding to a regular partition. Okay, so I will tell you how we should do this reverse engineering process. But first, let me remind you of a Riemann sum over a regular partition. Okay, let us consider that we have a closed interval, so from A to B, okay? So let us say that this point is A and is included, and this point is B. So I am looking at the closed interval from A to B, okay? Now I will start chopping up this interval into n equal pieces. N is any natural number, okay? That will actually give me a regular partition from A to B. Okay, so if I do that, for example, as we learned during the lesson, this is denoted by x0, and this last one is denoted by xn, and then of course the first one is called x1, the second one is called x2, and then dot dot, for example, we reach to xk minus 1 and xk, and then of course we continue. So this one that you see here is called the kth interval, yes, because this one is the first interval, the index is 1, this is the second interval, the last index is 2, so the kth interval should be the one with last index k. And then it is important to know that this point and that point are also included in this kth interval. So the kth interval is actually the closed interval from xk minus 1 to xk. Okay, and of course we know that the length of this kth interval is denoted by delta x sub k, and it is simply xk minus 1. But for the case of a regular partition, all of them are equal because I am chopping up the interval into equal pieces. So instead of denoting the length by delta x sub k, because all of them are the same, so I will just simply show them with delta x. And of course you know that this delta x is 1/n of the total length. In principle, the total length is b minus a, and I divide it by n. Okay. So then of course if I want to find a formula for each one of these what we call nodes, so the node number k is the beginning number, which is a, plus k times delta x. Yes, for example, if I want to reach to x1, I start from x0 and I add 1 delta x. If I want to reach to x2, I start from x0 and I add 2 delta x's. So if I want to reach to x sub k, I start from a, but this time I add k delta x's. So this is the formula in principle. It becomes k, and instead of delta x, I put b minus a over n. Okay, so that is the kth node actually. Okay, now if I want to set up a Riemann sum, let me say that I have a function, any function f, and then I want to set up a Riemann sum for this partition. So in principle, I want to tell you what is the Riemann sum of this function and this partition Pn. which is actually this partition. So let me write it here for you. So Pn is equal to x0, x1 up to xn. Okay? But for setting up a Riemann sum, I also need something which we call a tag, and it's a vector consisting of n components. So C is a vector with n components. The first component I denoted by C1, C2 up to Cn. But what are these numbers? These are just any arbitrary numbers chosen from the appropriate interval. For example, C1 is any number within the first interval. Minimally, it can be A, maximally, it can be x1, or if you prefer, you can choose any number within this interval. So what is C2? C2 is minimally x1, maximally x2, or if you prefer, some number in between. Okay? So in order to set up a Riemann sum, you need a function, you need a regular partition, and you also need a tag. A tag means a vector including n number of components. The number of components and the number of subintervals match. And then you can choose any number within that corresponding interval. But what you need to know, because the intervals include these numbers, includes the endpoints, so these numbers can in the extreme cases be the endpoints as well. So for example, C1 can be x1, the right endpoint, and C2 can also be x1 simultaneously, because x1 is shared between the first interval and the second interval. Anyway, now let us say that f is given, P, a partition sub n, a regular partition with n nodes is given, and you have chosen a tag. And now what do I mean by a Riemann sum of this form? So the Riemann sum of the function f corresponding to this regular partition P sub n and corresponding to this already chosen tag C is defined to be this sum. A sum of your function calculated at these tags, okay? So let us say any of them, and then multiplied by the length of the interval, which in this case all of them are delta x. If they are different, you have to put this delta xk as well, and then around your sigma k goes from 1 to n. Okay, so what you get is what is called the Riemann sum. But there is, as you learned during the lesson, if the function is integrable, the limit of this Riemann sum, any Riemann sum, as n approaches to infinity, becomes equal to the integral of your function on that interval that we are talking about. Okay, so in principle, if someone guarantees that the function is integrable on the interval we are working on, then the limit of these Riemann sums for any chosen tag, that's important, any chosen tag approaches to the value of the integral of your function on the interval from a to b. So that is the importance here. Okay? Okay, now as I told you in the beginning of this video, our goal is to interpret this sum as a Riemann sum. So far, there is only one commonality, and that is the sigma notation that you see here and there. So I have to fine-tune this f and of course my interval so that this sigma reads very, very similar to this sigma that you see, or even identical to this sigma you see. Okay. The first thing you have to do is to guess a function for it. Okay, for example, I see that you see this delta x. If you see the formula for delta x, you see an n below it, but the numerator of delta x is b minus a, the difference between the endpoints of your interval, which is still we don't know about it yet. But at least this 1 over n, if I write it here, it is b minus 1 over n, so we have one more commonality here because this 1 over n also appears here, so that's good. But now the first thing I think is good to do is to guess a function which would be somehow responsible to generate this part. And yeah, might be a rough guess because this is taking the third root. Might be the function comes to mind immediately is probably the third root function. Okay, so let us start to see how it works. Okay, if I insist that this is my function, then in order to generate f of ck, there is no, because I want to give the role of this part to f of ck. Okay, and I have already chosen, or actually this is an educated guess. Still, we don't know if it is going to work or not, but if you are patient, you will see it works, and then you get experience for the other problems coming. So here, I would say that this ck should be this number inside, yes? So that is my first guess. I would guess that ck is 1 plus 21k minus 20 over 3n. Why this is a good choice? Because if this is going to be really the function responsible for this Riemann sum, and if I choose this ck in this form, if I ask you what is f of ck, you will go to your function and replace x with ck. So you will get the third root of 1 plus 21k minus 20 over 3n. And this is exactly this expression, of course, written in fractional exponent. Yes? So that is also a good choice. Now, if both of them so far are correct, it is important for us now to be able to engineer this A and B. There is a very nice logic here. So if I ask you where is C1, according to what I told you, C1 is any number in the first interval, subinterval. So C1, let me emphasize, so C1 is somewhere here. C1 is in the first interval. And as you see that when I increase the number of n, because eventually I want to send n to infinity, when I send n to infinity, it means these delta x's become smaller and smaller, so this C1 will be closer and closer to A. So we expect that C1, as n grows large, approaches to A. Okay, so this is very reasonable. So I will calculate C1 here. So let me change my color. So I calculate C1 here. It means that I replace k with 1. So this becomes 21 minus 20, which is 1. It's 1 over 3n. And if I send n to infinity, what happens? The second term vanishes and I get 1. So my guess is that this 1 is going to play the role of my A. Okay, with the same logic, if I want to find B, I know that I have to think about Cn. Why? Because if you look at the last interval here, this is xn minus 1, you know that Cn lies somewhere here. And with the same logic, if I make n very great, and then this means that x sub n minus 1 are getting closer and closer to B, and Cn should also get closer and closer to B. So this means that if I calculate Cn, how? By replacing k with n, which is 1 plus 21n minus 20 over 3n, and take the limits, but before taking the limits, so let me write it like this. So I divide 21n divided by 3n, it becomes 7, and then minus 20 divided by 3n, which is 8 minus 20 over 3n. And now I send n to infinity. Yes, I send n to infinity. The second term would become 0, and it becomes 8. So that is a good choice for B according to this logic. So our guess is that the interval that we are working should be somehow from 1 to 8. Okay? But the important thing here is that we have to confirm that this ck is really an appropriate tag. What do I mean by that? Because do you remember I told you that each tag should be in the corresponding interval. So it is important to check if this is really a number within the kth interval here. Okay, so what is the kth interval? By the way, of course, if you, so let me tell you, so if x sub k minus 1, if you want to calculate it, you have to replace this k with k minus 1. So if I want to review, we actually guessed about the function and guessed about ck, and then using this strategy we are able to somehow guess the appropriate numbers for a and b. But then before continuing, I really have to confirm that this c sub k is really within the kth interval, otherwise I cannot say that this is a Riemann sum. In order to do that, I need to know the kth interval. So the kth interval is x sub k minus 1 to xk. Xk is this expression. For this problem, a we found it to be 1 and b we found it to be 8. So let me write this formula for xk appropriate for this problem. I replace a with 1, I replace b with 8. So it becomes 8 minus 1 over n. So this is just 1 plus 7k over n. So this is x sub k. X sub k minus 1, of course, will be 1 plus 7k minus 1 over n. Now what I have to confirm, that this ck is somewhere between xk minus 1 up to xk. So this happens if and only if, instead of x sub k minus 1, I plug this in, because I want to check if it is true or not. Otherwise, I cannot interpret that as a Riemann sum. I should write this is less than or equal, ck is 1 plus 21k minus 20 divided by 3n, and then is less than or equal to x sub k, 1 plus 7k over n. So this double inequality should be checked. And of course, checking it is not hard. First of all, you see that I can drop this 1 from all sides, and then I can multiply everything by 3n. Okay, so what happens? Then this becomes equivalent. If I multiply, after dropping 1s, if I multiply everything by 3n, the left side becomes 21k minus 1, and the middle one becomes 21k minus 20, and the right hand side will be 21k. Yes, but this is correct. Yes, because 21k minus 20 is definitely less than 21k, that's correct. But what is this one? This is 21k minus 21, which is definitely less than this one. So yes, this ck really belongs to the kth interval. So everything is in order now. But I have one simple problem. The problem is that delta x is not 1 over n. So what is delta x in this problem? So delta x is b minus a divided by n. But b is 8 and b is 8, a is 1 divided by n. So it becomes 7 over n. Okay? Okay, so but here I have a 1 over n. So what I have to do some adjustments, and that is easy because that's just a constant. So what I will do, I will actually multiply both sides by 7, and I calculate 7L. Whatever it is, I finally divide it by 7 to find my own L. Yes? So what I will do, instead of calculating L, I can calculate 7L, or of course you can calculate L like this. You can write 1 over 7, and then you can write limit n goes to infinity, and then I have sigma k goes from 1 to n. I compensate that 1 over 7 by putting a 7 up there, and then I have 1 plus 21k minus 20 divided by 3n, and then I have to the power of 1/3. Yes? But now I can write it as 1 over 7, limit n goes to infinity, sigma k goes from 1 to n, but instead of this expression, I can just simply write f of this ck. So it is f of ck and instead of 7 over n, I can put delta x. So this becomes delta x. But if you see, if I ask you, what is this? This is exactly your corresponding Riemann sum. So this becomes 1 over 7 limit of your Riemann sum. Okay? But there is no guarantee that the limit of the any Riemann sum exists unless you already know that your function is integrable on the interval that you are working on. And how can I guarantee this, for example? Because I go to this function and I go to this interval from a to b, which is here from 1 to 8, and I say that this function, this is indeed necessary in the exam. You should say that, okay, because this function is continuous on this closed interval, based on the theorem we had in the course, it is guaranteed to be integrable. And if now we know that this function is integrable, it means that its limit of the Riemann sum, no matter which Riemann sum we are choosing, approaches to the same limit, which is the integral of the function. So the answer will be simply 1 over 7 integral of your function, the third root of x dx, on the corresponding interval that we discovered to be from 1 to 8. So the bottom line is that we were able to interpret this limit as this integral. So it's a little bit of abuse of logic, you know, because if you remember when we learned about calculating integrals, we learned it by calculating the limits of Riemann sums in order to get integrals. But because of the power of a second fundamental theorem of calculus, now we are more comfortable in calculating integrals rather than calculating limits. So okay, we switch the logic. Now we use integrals to calculate some kind of difficult limits. Okay, so the only thing we have to do now is to calculate this number, and that number is exactly our limit. Okay? Okay, so this is very easy, so I can write it as 1 over 7, integral from 1 to 8, I write it as x to power 1/3 dx, but this is simple, so 1 over 7, x to power 1 unit more, 4 over 3, divided by 4 over 3, which becomes 3 over 4. And I have to run it from 1 to 8, so the answer will become 3 over 28, and then I have to put 8 to power 4 over 3 minus 1 to power 4 over 3. So this becomes 3 over 28, and then 8 to power 4 over 3. Instead of 8, I can write 2 to power 3. 3's are cancelled, so 2 power 4 is 16, minus 1 is 15. Yes, so it becomes 45 over 28, and that is the answer we're supposed to get. Okay, but before ending this video, let me just highlight one point here. There are some degrees of freedom that you might have in solving this problem, okay? So, for example, here might be, instead of choosing this function, for some of you this function doesn't look very natural for this problem, might be you guess a different function. For example, you might guess that, okay, I want to choose my function f of x to be 1 plus x to power 1 over 3. Yes, this structure is also very comparable to this structure. Yes, you have your 1 here, and then you have some variable here, so you just call it x, and then you have this power. So it might be, instead of guessing this function, some of you might guess this function. Okay, I just want to tell you that this is also working. But of course, in the previous case, you have to choose ck to be this, because this is supposed to be f of your ck, and if you choose this one, you have to choose ck like this. But if you already take care of 1 here, so the ck that you choose should also be different. It should be only 21k minus 20 divided by 3n. Okay, so let us try to solve this problem in this way as well. So let me take this with me to the next page. Okay, so if we do that, our duty is now to find the interval. So the same technique will work. So I calculate C1 by replacing k with 1, so it becomes 1 over 3n, and I send n to infinity. When I do that, I get 0 this time. So a instead of being 1 will become it becomes 0 this time. Instead of being 1, it becomes 0. And then for finding b, I calculate Cn, so I go here, I replace k with n, so this becomes 21n minus 20 over 3n, and I can do as before, so I can write 21n divided by 3n 7 minus 20 over 3n, and then I send n to infinity, then the answer becomes 7. So this time b is not 8 but 7. So this means that the interval that I guess is from 0 to 7. And then of course I have to confirm now that this ck is indeed in the kth interval. So what I do, I write the formula for x sub k, which is a plus k times b minus a over n, but this time a is 0 and b is 7. So it becomes 7k over n. And then of course x sub k minus 1, I just replace k with k minus 1, so it becomes 7k minus 7 over n. Yes, so I replace k with k minus 1, and then I multiplied 7. Now I have to really confirm that this is indeed true, that xk minus 1 is less than or equal to ck is less than or equal to x sub k. I have to double check this. Okay, but let me simplify to see if this is true or false. Instead of x sub k minus 1, I can put this expression, and instead of ck, I can put this expression, and instead of xk, I can write that. So this becomes 7k minus 7 over n, less than or equal to 21k minus 20 over n, over 3n, sorry, and less than or equal to x sub k, which is 7k over n. Okay, to understand that this is true or not, let me simplify it equivalently. Let me write here. So let me clean this. Okay, so what happens to understand that? I multiply everything by 3n. When I multiply the middle one by 3n, I am left only with the numerator. So 21k minus 20. Less than or equal. If I multiply this by 3n, n and n cancelled, so it will be 21k. And if I multiply the left hand side by 3n, n and n are cancelled, so 3 will be multiplied here. So it becomes 21k minus 21. Is this true? Definitely yes. 21k minus 20 is definitely less than or equal to 21k, and 21k minus 21 is also definitely less than this one. So yes, this is true, and this means that this is indeed true. Okay, so everything now is in order. So now if I want to write my limit, okay, I also need to calculate delta x, so let me calculate delta x, which is b minus a over n. In this case, it will be 7 over n, because b is 7 and a is 0. And then the same problem arises again. You see, I have only 1 over n, but I need 7 over n in place, so it motivates me exactly to do the same thing. So I would write 1 over 7, limit, and then I have sigma, k goes from 1 to n. This expression will be this function calculated at this ck, so it is just f of ck, and delta x is and now delta x is here, yes, because I multiply by 7 and I divide by 7, so this is 1 over 7 that you see here, and 7 over n is just delta x, and that is exactly your Riemann sum. So this becomes 1 over 7, n goes to infinity, of course, the limit n goes to infinity of our Riemann sum, but for this new function. To be honest, it was better to call this a different function, yes? I should have called it g, for example, because this function is different, but forgive me for that. So I would write just f and p sub n and a new set of tags, okay? But again, as before, this is the limit of a Riemann sum. So we realize that this sum is a Riemann sum, and this L is a limit of a Riemann sum, of course, divided by 1 over 7. But now again, as before, you go back and say that this is the function, and this is my interval. This function is continuous on this interval, and because of the theorem in the course, continuity implies integrability, so the function is also integrable. And if the function is integrable, doesn't matter which Riemann sum I am looking at, the limit of all those Riemann sums approach to the same limit, and that is exactly the value of the integral over the the value of the integral of the function over the corresponding interval. But in this case, the integral will go from 0 to 7, but the function is 1 plus x to power 1 over 3 dx. Okay, so apparently what we get here is different from the integral we got before, but the answer of this integral will be the same as before. And of course, you can immediately see that if you want to calculate it, for example, let us do u substitution. Let me introduce u to be 1 plus x, then du becomes simply dx. And because x goes from 0 to 7, this would imply that u goes from, if x is 0, yes, u becomes 1, and if x is 7, u becomes as 8. So it becomes from 1 to 8. So this means that that limit becomes 1 over 7 integral from 0 to 7 now goes from 1 to 8, and instead of having 1 plus x to power 1 over 3, I just simply write 1 over u to power 1 over 3 du. But that is exactly the same integral we calculated before, but in the previous case, instead of variable u, which is a dummy variable in a definite integral, as I have described in the lecture notes, so this will be the same value as before. So it doesn't matter if you calculate that one, you will again get the same number. What was it? 45 over 28 again. So this is also an important thing. So you see that both solutions that you see, I mean, I have chosen different functions a little bit and different expressions for c sub k, but both of them will work fine, okay? I hope that this video was useful for you. Until the next video, be safe and goodbye. Thank you.